I'm Daira Hopwood. I work for Zcash. Use ZK pronouns. That's my details. So these slides are at this URL. And what I'm going to talk about is how to design circuits for proving systems that use R1CS. So R1CS is a low-level language based on constraints that you can use to program some proving systems. Okay. So in general, what is a zero-knowledge proving system? I'm not going to spend very much time on it because I suspect most of you know. So we have a statement that we want to prove, and we have some instance variables that the statement depends on, so there's a public, and some witness variables that are private. And the fact that the proving system is zero knowledge means that all we prove is that we know the witness variables. And we don't give any other information than that, and the statement is true for those witness variables. Okay? And the type of proofs that I'm going to talk about are non-interactive proofs. So you don't have to engage in a protocol with an interactive protocol with the prover. The prover just sends you a proof, you verify it. Okay, so there's an important distinction here that we need to understand. These are proofs of knowledge, which means I know the witness, I'm not just proving that the witness exists. And that's important for practical protocols, because suppose I want to prove that I own a coin in Zcash. Zcash is a cryptocurrency that uses zero knowledge. So I would have to prove that I knew the secret key associated with the coin, and it wouldn't be sufficient just for me to prove that the secret key exists, because it could be someone else's coin. So these arguments of knowledge are more useful in practice for building real-world protocols. Okay, yeah. There's lots of other details that you can probably find other tutorials on, but I'm not going to focus on this talk. Can everyone hear me, by the way?
Yes.
Good. So, for quite a long time, ZK proving systems were considered pretty impractical. They were mostly considered an academic thing. But since 2013, there was a breakthrough system called PHDR, or Pinocchio, which sort of made this practical enough and efficient enough that we could use them in real protocols, basically. It's a bit of an oversimplification, but basically true. And so the whole field has taken off since then. So I work for Zcash. It's a fork of Bitcoin, but in Bitcoin the ledger is completely public, whereas in Zcash all of the amounts, the senders, and the recipients, so the transaction graph, is completely hidden. So we can use Zcash as an example of the kind of statement that we want to prove in zero knowledge. So this is simplified a bit, but the statement could be roughly, I know the private key, so values stored in notes. Notes have nullifiers, which is how you prevent double spending, and I'm showing that I know the private key, that means I own that note, and the transaction balances. So that's an example of what we might want to prove in a practical protocol. Okay. Yeah, so we're focused on proving that cryptographic protocols have been followed correctly. That's the most useful real-world application. So usually you design a protocol using conventional cryptography, and then you run into an obstacle that you want to prove that that some condition holds, but you don't want to give any information about it. So in the example of Zcash, we don't want to give away what the amounts are, but we want to make sure that the transaction balances. So the zero knowledge here is a very powerful primitive because you can prove that you're not giving away any information other than the statement you're proving. So then you can analyze the statement and say, okay, I might be giving away some metadata, but I know exactly what that metadata is. I can reason about how much I'm giving away. So the kind of things that we might want to include in our statements are just the things that we use in cryptographic protocols. So hash functions, one-way functions. So this is an elliptic curve multiplication used in public key cryptography. This is base points, secret key, public key. And we also need some things that are easy when you're computing in an ordinary programming language, but are kind of tricky to express in these constraint systems. So things like the type, so you have bit strings, integers in a particular range. You need basic arithmetic and logic, and conditionals. So these are circuits. You can think of them as analogous to Boolean circuits, but they operate on field elements. I'll explain that in a minute. Another thing that you might want to prove is you can build up a tree of proofs, and in one proof you can prove that another proof is valid. So that's useful because the top level of the tree, you end up with a very succinct proof for a lot of different statements. So how do we express these statements? Can't express them, well, we can, but there are systems that will compile something similar to C to an R1CS statement, but they're very inefficient. It's much more efficient if we consider the native language of the proving system, which is something called R1CS, and if we do that, then we will end up with a much smaller representation of the statement, and it will be much more efficient. Because, so if you consider Zcash as an example, the first iteration of it would take about 40 seconds to make the proof needed to spend a note. Now, obviously, 40 seconds is quite a long time if you're twiddling your thumbs waiting for a payment. And it makes it impractical on mobile devices, things like that. It also took a lot of memory. So if you optimize the representation of the statement to reduce the number of constraints, then your protocol will be much more efficient. So here are some examples of higher level programming languages that would compile down to this low level representation. So we have Bellman, which is a Rust library, and that's what Zcash uses. That was written by Sean Bowe mainly. We have Snarky, which is developed by O1 Labs. And Coda is another cryptocurrency that uses this. It's based on OCaml. And we have Socrates, which is used in the Ethereum community mainly at the moment. So that's a specialized DSL. And they compile down to the language that we're going to talk about in this talk. Because even if you're writing your code in these higher level languages, it's extremely useful to know R1CS in a similar way to it being useful to know assembly language when you're doing ordinary programming, if you want to write efficient code. But even more so because in assembly language, it's fairly well abstracted. The low-level details of the processor architecture don't leak too much into the high-level language, so you can write C and compile it to almost anything. But for R1CS, some of the details of the R1CS layer are going to leak up into these other languages. In particular, so, okay, that's what I was saying now. So the reason we want to learn R1CS, besides that, is it's used by lots of different proof systems. So you've heard of bulletproofs and Groth16, BCTV 14, which is the original system that was used by Zcash. Groth16 is the newer one. Some new systems like Sonic, they all use R1CS, or close variants of it. Okay. So you should think of this as a compilation target, and eventually we're going to have the tools needed to write all of our statements in higher level languages. But this is still going to be useful to understand the lower layer. So an R1CS description is basically just a bag of constraints. There are no abstraction mechanisms, there are no functions. You're going to have to rely on whatever higher level language you're doing to avoid having to sort of repeat the same statement over and over again. But you can get a good idea of what the cost of a circuit will be by kind of doing the compilation in your head. Another thing about it is it's very error prone. So if you want to do integer arithmetic and you're representing that in terms of field elements and the arithmetic overflows, then you'll get the wrong answer relative to what you wanted. And for a security protocol, obviously that's bad. If you miss anything out, then that's probably an attack. Okay. So this is basically what we want to be doing. Designing R1CS programs is basically a cryptographic protocol design. So you will start with the protocol that you want, or a rough idea of what it's going to be. It will need one or more statements. So, for example, the current version of Zcash has 3 different statements used in different parts of the protocol. You will then translate that to R1CS. There may be some other language in the middle here. But in order to inform your protocol design, you will have some prior knowledge about what various primitives are going to cost. So you will avoid, when designing your protocol, things that you know will be very inefficient. So you end up with this R1CS translation. It could be just in your head, and you could have just done it for the parts of your circuit that are taking up the most constraints, so the most performance critical. And then so you justify any assumptions that you've made in that translation. So we're going to see some examples of that. When you're doing, for example, elliptic curve arithmetic in circuits, there's a lot of math that is used to justify the optimizations that you did. So you optimize in the feedback loop here And you will need to do more math in order to justify those optimizations. And that will feed back to your statement design, the protocol design, because you may need to assume something here that your protocol didn't guarantee. So you need to change the protocol to make it work. And then, so as you're doing this, you can write up any good ideas you have so that you can use them or other people can use them. You look in Appendix A of the Zcash protocol spec. It has a bunch of, it has so a lot of the content of this talk actually. So you can start with that in your protocol design. Okay. So the types that you're operating on in your circuit are, the basic type is a field element. And so who already knows what a field is? Okay, about half the audience? Okay. So a field is basically a kind of number that supports, it's a set of numbers that supports addition, subtraction, multiplication. Those are closed operations, so they result in another field element. And inverses or division. So here are the algebraic rules that a field follows. You have sort of the properties that you might expect for the integers also work in fields. And so inverses is an interesting one here because we don't have an inverse for 0, but we have an inverse for every other element in the field. So that's not true of the integers, for example, because take the integer 2, then a half is not an integer. So division, taking inverses on integers is not closed, but it is on fields. Okay. So the fields that we're going to use are finite fields, so integers modulo prime. So, for example, the integers modulo 13 would form a field. And the reason we use finite fields is so that we keep the values that we're representing small. So they will need to be of a certain size in order to maintain security, typically about 256 bits. But when you operate on, say, you add 2 field elements, or multiply 2 field elements, you get something else that is also only 256 bits. So that the size of the representations doesn't blow up. And that's basically why we use finite fields so much in cryptography. About 255 bits. But that means that we have to be careful of overflow because remember, an attacker is choosing the inputs to your circuit quite often. So they can deliberately choose a value that is close to overflowing. You can use them to represent bits, so 0 or 1, but you're basically representing 1 bit using 255 bits. So that's quite inefficient, and you want to avoid it, but often you can't avoid it. And you can use them to just represent themselves, field objects. So in elliptic curve cryptography, for example, so this 255 bits is an ideal size for the coordinates of elliptic curve pairs. So we can arrange that this prime is exactly the prime that we need for a particular elliptic curve. Who knows about elliptic curve cryptography? So basically, most of the audience. Okay, that's good. That's good. So our constraints are of this form. So A times B equals C, where each of these is a linear combination of variables. So remember that we had instance variables and witness variables. So these can be any linear combination of constant times variable plus another constant times another variable, and so on. So I'm going to use a convention in this talk. It's also used in the Zcash protocol spec. We use this symbol for the multiplication when we're talking about the multiplication of a constraint. And we use a dot when we're talking about a constant multiplication. That's basically just, it's easier to keep track of what a set of equations costs if you distinguish between those two operations, even though mathematically they're the same. Okay. And the cost of our circuit is going to be roughly just the number of constraints. Notice that doesn't really depend on the complexity of the linear combinations. So we could have an arbitrary complex thing here, here, and here, and it would still count as just one constraint. That's just an approximation of the cost model, but it's a pretty good approximation in practice. Okay, so here, for example, is this is a particular circuit that we use in Zcash. It's a simplified version of it, actually. And the vertical axis here is proving time for our statement. The horizontal axis is roughly the size of our circuit. And don't worry about the exact numbers, just the shape of the graph that's important. So you can see these, it's basically linear, but you have these jumps, and these are at powers of 2 number of constraints. So if you're just above a power of 2, then try really hard to optimize to get below the power of 2. So we're talking about a constraint language. It's a little bit like a functional language, but it's a generalization of that. How many people have used relational languages? Almost no one. Okay. Yeah, because they're quite rarely used. I mean, things like Prolog, but because they may be taught in universities, but they're not used very much in industrial practice. But don't worry about that. The important thing here is you're just asserting that this is true, and you're not predetermining which is the input to the constraint and which is the output. You're just asserting that the relation holds. So, for example, you might be able to use the same subprogram in 2 different directions to do a conversion. Okay. Yep. Oh, everything's referentially transparent, so that means there are no side effects. There's no I/O. You're just asserting that a relation between the witness and instance variables is true, or that we know the witness variables. And there's no ordering of constraints, so we just have a big set of constraints that must all hold. And that's quite nice mathematically, because it's a symmetry on the program that you don't have to worry about the order thing, as you do in a sequential program. So let's have a look at some examples. We can prove quite easily that this is computationally complete, so we can express any Boolean circuit of a given size. So the way we prove that is, this is one way of doing a Boolean constraint. So we can see how this works. If x times y equals 0 means that either x or y is 0. So here we have 1 minus b is 0, so b must be 1, or b must be 0. So we can see intuitively that this is implementing a Boolean constraint. And similarly, we can express and, that's just a multiplication, and not is 1 minus b. So just using that, you probably know from complexity theory that and not are complete for Boolean circuits. So that just using those two operations, you can express any Boolean circuit. But that doesn't tell us how to do it efficiently, because we already said that just converting everything to Booleans, as you would when you're doing, say, an FPGA implementation or something, would be a very inefficient way of doing it. So the hard part is making use of the fact that we have an arithmetic circuit, so a circuit on field elements rather than Booleans. And we need to do that without making it so complicated that we make mistakes and we introduce security bugs in our protocols. So, yeah, just to give you an idea of how much the potential efficiency improvement is available relative to doing it just using Booleans. If we were to express the multiplication, just as we were doing a hardware circuit, it would take roughly 34,000 bit operations. That's a number that I got from one of Dan Bird's science papers, so it may be, it's the right order of magnitude. But in an arithmetic circuit, we can do it in just one constraint. So that's the potential improvement we can get. Okay? So let's start with some basics. We already saw that A times B equals 0. Remember that these can be arbitrary linear combinations, and implement A equals 0 or B equals 0. And we can generalize that fairly easily. So it's a common pattern that if you can prove that something is 0, then you can prove that two things are equal. And notice that this OR there, we didn't convert this expression to a Boolean expression on that one and then OR them together explicitly. We just represented it in a single constraint because that turns out to be 3 times more efficient. So you need to use the fact that it's a constraint language rather than converting everything into Boolean expressions. So there can be several ways of doing the same thing. So this is another way of doing a Boolean constraint because this is true for 0, it's true for 1, and it's not true for any field element, for any other field element. So that also works as a Boolean constraint. And in practice, you'll probably settle on a few specific ways of doing things, or the compiler from your higher level language will. But it's useful to know other ways of doing the same thing, in case you see them from other people's work. So, we've seen how to prove that something is 0, or that two things are equal. What about if they're unequal, or not equal to 0? So, use the fact that 0 is the only field element that doesn't have an inverse. So if we can show an inverse here, an inverse of A, then we know that A is not 0. So notice how for this subsection of a circuit, we also have our witness variables and instance variables. So we can represent the structure of circuits sort of recursively. Part of a circuit looks like another little circuit. And this needs the witness variable because it needs to be private. Because otherwise we would be leaking information about A. Okay? And similarly, if we can say something is not equal to 0, then we can do an arbitrary inequality. So how do we do division? Well, because this is a constraint language, we can convert any division into a multiplication. So if we multiply each side of this by b, we get A times B equals C. But you should be worried about what happens here when B is 0. Because if B is 0, then we constrain C to 0, but A could be anything, because anything times 0 is 0. So that probably isn't what you wanted to do if you just wanted division. So you have two options: either prove that this doesn't happen for your particular circuit, or just use what we said in the previous slide to prove that to constrain the denominator not to be 0. And notice that because we're implementing this in terms of multiplication, it's exactly the same cost. Whereas a lot of the optimization of elliptic curve crypto systems, for example, outside a circuit, is based on reducing the number of inversions because they're very expensive. They might be, say, 100 times the cost of multiplication. But here, you don't need to do that. So you're changing some of the trade-offs that will have been used in other implementations of the cryptography you're using. Okay. So that can, you might choose different representations of things or different algorithms in order to make use of that. Okay. So that was just a special case of a more general principle that you can invert any function. So f is invertible, then we can apply f to both sides. We get f of y equals x. Okay. So, for example, if you want to prove that you have a preimage of a hash function, you don't have to represent the inversion of the hash function. You just implement the forward direction, or whichever direction is easiest, actually. Okay. So, Boolean operations. Often we can implement sort of an n-ary operation, so an operation with n inputs, faster than the obvious way, which is just to collect the inputs one by one. So you can implement A and B and C, for example, as A and B, and then AND the result with C. But there may be a more efficient way of doing it. So, can we do better? So the final answer is going to be Boolean, so let's constrain that. And if the result is true, then all of the inputs must have been true, to pass the definition of AND. So let's just sum them up. Because we know that this isn't going to overflow in practice because the number of inputs is not going to be 2 to the 255. We couldn't represent a circuit that big. So you can just add them up and subtract from n, and then notice if all of these were 1, then n minus the sum is going to be 0. And then, so that's saying, if this was 0, then this wouldn't be constrained at all. If this is 1, then we're constraining this to 0. So we've implemented half of the specification of AND here, and then we can implement the other half of the specification like this. So this is the kind of the tricks that we can use to, in this case, implement an n-ary AND for any n in just 3 constraints. And there are lots of tricks like this. So that what we've done here is we haven't constrained ourselves to treating Booleans just as Booleans. We can take advantage of the fact that they're represented as integers. Okay, and we can do OR in the same way. Simple. So another common operation that we might need is constraining an integer to a range. So for example, suppose you want a transaction to balance. So you want to prove that the inputs sum up to the same as the outputs, so that you haven't destroyed or created any money. If you don't prevent overflow, then an attacker could choose the inputs and outputs so that they appear to balance, but actually one of them is, say, close to the prime of the field that you're using. So range constraints are important because if you can prove that an integer is in range, you can then use it in arithmetic just as an integer rather than as a field element. So how do we do this? Well, the easiest way to do it, just for, we have a range that's a power of 2, we Boolean constrain the binary representation, and then we sum these, because this is just a linear combination, and say that's equal to our original value. Notice that we're multiplying something by 1 here. It turns out that multiplying something by 1 can always be optimized away, because we can just substitute into wherever we use A. So if we use A here in a different constraint, we could just write this expression instead. And there's a more, if we don't have a power of 2 range, then there's a more complicated way of doing it, which depends on the bit representation. Basically what we're doing there is representing it as a Boolean circuit and then optimizing it, specializing on the range that we want to constrain it to. And we can do other Boolean operations in a similar way. Basically, if you have some funky constraint and it's supposed to be representing a Boolean operation, because you can just look at its truth table and check that it's true for every possible input, because you only have a small number of possible inputs, so just checking the truth table is a way of checking it's correct. Or you can try and understand what it's basically doing. So this is basically saying that exclusive OR is a bit like addition, but with a special case when both of the inputs are true. Now, when we try to do an n-ary version of this, it turns out that we can't do it in a fixed number of constraints like we could for AND or. And there's a reason for that, because the truth table of an exclusive OR, it has half the outputs are 0 and half the outputs are 1. So unlike, say, the truth table of AND, where you only have a single output that's 1, so that more complicated output pattern is what requires you to use more constraints. Because you can't just special case the only combination that gives a different answer. Okay. So this is actually turns out to be logarithmic in the number of bits. So we also need to be able to implement conditionals. Now, in an ordinary programming language, and say if some condition, then some piece of code A, else some piece of code B. You can't really do that in a constraint system. Or rather, the cost of it is going to be the size of A plus the size of B. So you can't get away with conditionally paying the cost depending on what the truth value is. So what you would do to optimize it in practice is to try and merge the pieces of code A and B and try and find commonalities between them so that you're not just duplicating them. But the simplest possible form of conditional is just a selection constraint. So this is the notation you would use in C. You're choosing either X if B is true or Y if it isn't. And it's fairly easy to see that this works because if B is 0, then you're saying that Y minus G is 0, and so Y is equal to C, which is half of our specification. And then if B is 1, then Y minus X equals Y minus C, so X equals C. I'm British, but I've been so Americanized that I say Z all the time. Yeah, so that's what that says. Elliptic curves. Elliptic curves are fun. Some really fun maths. We established that most of you knew what elliptic curve cryptography was, and it's useful because not only can you do public key cryptography, you can also do some secret key cryptography quite efficiently, or symmetric cryptography. And it turns out, remember we said before that if you match the prime used for your field to the prime used for the elliptic curve, then you can get very efficient elliptic curve arithmetic. So here are the real numbers. SHA-256 is a conventional bit fiddling hash function. It takes about 27,000 constraints. And a kind of functional equivalent for some uses, not for all uses, takes only 864 constraints. But this doesn't Boolean constrain input. You need to keep track in your head of which things have been Boolean constrained. And if you make a mistake there, then, well, if you Boolean constrain them twice, it's not harmful, it's just inefficient. If you end up not Boolean constraining them at all, then you have a security bug. So it's probably worth saying, this Peterson hash is collision resistant, but you can't use it for some of the other things that you could use a hash function for. So you normally could use a hash function like a pseudo-random function, but you can't do that in this case. Okay. So notice that normally outside the circuit, if you're doing elliptic curve crypto, it would be more expensive than with this hash function by quite a long way, but that situation is reversed. I should say, by the way, that there are some proposals for how to do efficient algebraic hash functions, and quite recent ones. One that's going to be published, I think, next week, that will reverse the situation again, and you will be able to do symmetric crypto very efficiently in the circuit. But I don't think I'm allowed to tell you how performant it will be. I've been sworn to secrecy for this okay, so what an elliptic curve is it's kind of a plane curve, so a curve in 2 dimensions. This is a drawing of it over the real numbers, or a drawing of a particular curve shape over the real numbers. In practice, of course, we're using finite fields so that the representations don't blow up, as I said before. But drawing these shapes can sometimes give you an intuition that helps you understand how it behaves over fields as well. You can be misled by that, but sometimes it's useful. And notice how similar this equation is to the equation of a circle. There's basically a deformed circle. And this term here is expressing the deformity. But you don't really need to know that. It's just fun. So, Edwards curves are a very popular curve shape because you can implement them without special cases. So, for some types of elliptic curve shape, you have something called a point to infinity, and you have all of the curve equations have to be. You have to list a bunch of cases depending on whether the inputs are point to infinity. So for Edwards curves, you don't have to do that. So they're very nice. And remember, conditionals are really expensive in the circuit, so we want to avoid conditionals as much as possible. There's a way of, so if you just write down the equations as you would find them in one of these papers that defines the curve, the obvious way of doing it is having constraints, and then you can get that down to 6 or 5 by rearranging things. And because this is going to be the bottleneck, it's going to be the determinant of the overall efficiency of your circuit if you're mostly using elliptic curve operations. The difference between 7 constraints and 6 or 5 constraints is, well, this is 14% and this is 28%. So these kind of shaving off a constraint here or there can actually be quite significant. Okay. And as I said before, you can do divisions very efficiently, so that means that you can use some of the simpler equations. So if you know the difference between affine and projective coordinates, outside the circuit you would normally use projective coordinates or Jacobian, but here you can use the simpler affine ones because inversion is efficient. Okay. This is another kind of curve shape that is quite popular, and it turns out that there's an equivalence. I don't know why it hasn't drawn the Edwards curve here, but there's an equivalence between Montgomery and Edwards curves, and you can sometimes use that and switch between the two representations within the same protocol. So what Zcash does, for example, is all of the interface of the circuit to the outside world. The statement is expressed in terms of Edwards because that's simpler to use, and then the internals use Montgomery, and we proved that the special cases that I talked about before don't occur. Because they can't occur, you don't have to handle them in the circuit, so that doesn't cost more constraints. Yeah, that's basically what I said there. Doing this kind of thing, you have to be an expert, but basically there will probably be libraries that you can use that have already done these optimizations, so you will only have to consider the higher level operations like, for example, scale multiplication, which is what you use, for example, to generate a public key from a private key, and what you use for Diffie-Hellman key exchange. But those will be packaged into reusable components, and hopefully they will have sensible interfaces and you will not have to consider any of this low-level detail. But if you do want to consider the low-level detail, it is really fun. And there are probably some other I think if more people were working on this, we could find more improvements. Because it's quite accessible math, really. So here, for example, I've improved this recently. So this value here is now 1300, I think. So we started here doing, if this is an arbitrary point rather than just a fixed space, then this operation typically would cost 3200 constraints, and we can get it down to about 1300 using a technique that I only discovered a few weeks ago, so it's not written up on these slides yet. But it's on the Zcash GitHub, if you want to know about it. So if you're doing these optimizations, you will need to make proofs. So if you look in the Zcash protocol spec in Appendix A, it doesn't just sort of hand wave saying this is a way of optimizing this. It will give a theorem saying that this optimization is equivalent to the original. You absolutely need to do that, because you will make mistakes if you don't. I'm not saying that you necessarily need to use formal theorem provers, because there's quite a steep learning curve for those. But if you just do the proofs by hand, that's actually fine in practice. Do things about things that aren't obvious to you, or that if someone was reviewing your implementation, that they would go, what the hell is this? So hopefully you get security audits done of your cryptographic protocols. If you don't, then that's kind of inviting security bugs. Okay. So one reason why people are worried about doing mathematical proofs of programs is that they think that the proofs will be invalidated when you change the program. But if what you're proving is that an optimization is correct, then those proofs tend to stay valid. You may have to adjust them, but you won't have to redo all of the work again. So it's really worth doing. Okay. We're nearly done. This is an interesting thing. So remember how I said that if you had a tree of proofs and you have a statement that proves that another zero-knowledge proof validates, then you can put them in a tree and you can use a very succinct proof to prove lots of things. So Coda is a blockchain system that uses this principle. And what it will do is you have a proof that is representing the validity of the head of the blockchain, so the last block. And that indirectly proves that all of the other blocks only contain valid transactions. So if you think about what that means for a light client for the protocol, a light client only has to download a small amount of information and it's validating the whole chain. It's a little bit more complicated than that in practice, because if you want to, for example, spend something that was created in the previous block, you have to update the proofs. So typically these will be represented in Merkle trees. You have to update the Merkle tree, and that requires more information than just the final proof. So applying this idea to practical protocols ends up being quite involved, but the basic idea is very pretty. So I improved this even further. You now do a pairing in 2000 and something constraints. And this GUT16 validation, GUT16 is a proof system, can be done in about, so it turns out to be more efficient to validate a batch of proofs at the same time, and that costs 20,000 constraints for the first proof, and then 5,000 for each subsequent proof. So if you remember, I said that SHA-256 costs 27,000 constraints. It's less costly to recursively validate a proof than it is to do one SHA-256 hash. So it's actually really practical to use this in real-world protocols. Okay, so we're nearly done. I find it really interesting and fun to do R1CS optimization. Maybe I'm weird, but I hope I haven't bored you to tears, and I've sort of convinced you that this is an interesting language, and also that it's a very error-prone language. So you need to be careful that you're not introducing bugs when you do optimizations. And so we can imagine tools that would improve this process a lot. So imagine tools that do model checking on constraint programs, or that prove that when you do an optimization, you have the same dependencies between variables as you had in the original program, because if you don't, then you definitely made a mistake. Okay. And this URL is wrong, that should be R1CS. Okay. Are there any questions? Yes.
So you mentioned that writing the programs is fun. How long would it take for you to write something, let's say, useful?
Not very long. So if you use something like Socrates, then you can basically knock up a circuit in an hour or two and be fairly convinced that it's correct. Or Snarky, or one of these other languages. Probably not Bellman. Bellman requires you to know Rust and to know a particular API, and you've got to have a bit more experience to do that correctly. But some of these DSL-based systems, they're pretty easy to use, actually. So a real-world protocol like Zcash and the Zcash spend circuit was developed over months and months. So it probably took about 4 months from the first writing down. So let's go back to that diagram. There we go. So the overall protocol design probably took around 8 months, and then maybe 3 months of that was iterating on the statement and doing optimizations, and writing the theorems to justify them. So does that answer your question? But toy examples are much, much easier. Any more questions? Yes.
This last slide that you saw, you said relations, choice of fields, right? You said
yes.
Choice of. How do you choose the field? Can you actually, depending on your use case, choose your field? Can you actually use 2 different fields and 2 R1CS somehow?
So the answer to that is quite complicated and depends on the proof system. So for some proof systems, like bulletproofs, for example, you have a fairly free choice of the field. except that it needs to be, so the fields that you're writing the R1CS in, the prime for that is the order of an elliptic curve group, so the number of points in the group. So you basically have to choose one elliptic curve such that you have another secure elliptic curve defined over the scalar field of the original one. If you're using, so that sounds complicated, but if you can ask people how to do it, you can look online how to do it. It's not that hard. If you are using a proof system like Correctness or BCTB 14 or Sonic, then you're going to have to create a pairing friendly curve, and then another curve that is based on the order of the pairing. That's a little bit more complicated, but so in practice you can use ones that people have constructed already. So Zcash uses a pairing called BLS12381 and has an embedded curve called JobJob. So if you just use those in your protocol, then you'll be fine, because those are specifically designed to be used together.
One small question about the trusted setup. Could you make some comments about vulnerability?
Oh, yes, okay. So Zcash originally used a proof system called BCTB 14.
What was the question?
So you wanted me to comment on the vulnerability that was present in Zcash, which could have allowed you to forge Zcash. So when we launched the protocol, we used a proof system called BCTB 14 that had been published a few years earlier, but that never had a security proof. It was based on a previous system that did have a security proof, but there were some modifications needed for both for efficiency and for to adapt it to asymmetric pairings. So in practice, we couldn't use this earlier system that had a security proof. The protocol that Zcash is based on, called Zcash, had proposed using this proving system. Basically, the authors of the Zcash paper, they were the people who were experienced in the cryptocurrency protocols and people who were experienced in proving systems, but the proving system had this flaw. The flaw is not really specific to trusted setup. What happened was that if you're doing a trusted setup, then in order for people to trust it, you don't want to just do it on one computer and trust one person to delete the information provided to both groups. So you do a multi-party computation. You use several computers, several people. You try to make them as independent as possible so that they won't. At least one of them will follow the protocol. So in order to prove that you follow the protocol, there's something called a transcript, which is basically it's the set of messages that the participants send to each other. So the bug was that transcript included some things that it shouldn't have included, and they aren't actually used by the proof system, so they never should have been in the transcript. But there was it was an error in this BCTB 14 paper. But even if that error actually occurred in some implementations that didn't implement for multi-party computation. So, for example, JSNARK had this bug, even though it doesn't implement the MPC. So it wasn't specific to the MPC. That's just how it manifests itself. Does that?
Think about Starks, because I've seen it.
Yeah, so Starks are a system that doesn't require a trusted setup. So basically, for any of these systems, you need something that is going to determine which statement you're proving. So for systems without a trusted setup, you can construct this just using hash functions. You can have reasonable confidence that no one backdoored the hash function because it has a public design, and so it's called a reference string. It's just a list of random numbers. So that's the case for Starks. So that means you don't need this multi-party computation setup. But Starks have much larger proofs. Do they have more expensive verification as well? In practice, it's the size of proofs that is the obstacle to using Starks in real-world protocols, but there are some applications for which the proof size is high.
Yeah, hi. I first became interested in proofs from here about Zcash and kind of project development. As these kind of technologies are moving more into other cryptocurrencies, whether that's new cryptos or being integrated into existing ones, how do you see that affecting Zcash? And do you think that it's good from an academic perspective because it's bringing more people to the field, or do you think it's dangerous because it's bringing more people that can make error-prone security?
Oh, there's a question. I think it's good to put more people understand this stuff. It's like if you think of that, it's not specific to zero-knowledge proofs or to complicated cryptography. That if you have lots of newbies entering the field, then they're going to write insecure stuff. Think of the web. Think of people writing web services. We wouldn't say that it's a bad thing. Is it a bad thing that there's so many inexperienced people writing web services? But I don't want to be elitist about this. Overall, I think it's an extremely good thing that more people are learning this stuff. And maybe that will act as a catalyst for us to build more robust tools that it's a little bit harder to shoot yourself in the foot with.
That was the last question. Thank you guys very much.